Welcome to our presentation on mass storage systems. Today, we will explore various types of storage devices and their functionalities. Mass storage is distinct from memory, as it retains data even when the computer is turned off. It is sometimes called auxiliary storage and includes devices like magnetic disks, solid-state disks, and magnetic tapes. Magnetic disks are storage devices that use magnetization to read, write, and access data. They consist of a moving head disk mechanism. Magnetic disks have multiple platters covered with magnetic media. Each platter has working surfaces divided into tracks and sectors, with data read by read-write heads. The storage capacity is determined by the number of heads, tracks, sectors, and bytes per sector. Magnetic disks operate at high speeds, with positioning time, rotational latency, and transfer rate affecting performance. Head crashes can occur when the disk head makes contact with the disk surface. There are different types of magnetic disks, such as floppy disks and hard disks. Floppy disks are small and have limited storage, while hard disks hold more data and are faster. SSDs use memory technology for fast data access and have no moving parts, making them faster and more reliable than traditional hard drives. They are more expensive per megabyte and connect directly to PCI. Magnetic tape was an early secondary storage medium, holding large quantities of data. It is mainly used for backup and storage of infrequently used data, with typical storage ranging from 200 GB to 1.5 TB. Disk drives can be attached directly to a host or to a network. Host-attached storage uses I/O ports, while network-attached storage and storage area networks use network protocols for connectivity. Local disks are accessed through I/O ports, with common interfaces like IDE and ATA. High-end workstations use SCSI disks, which support multiple targets on each bus, and fiber channel for high-speed operations. NAS provides storage over a network, typically using file systems like NFS and CIFS. It is implemented via remote procedure calls over TCP or UDP, allowing easy access to storage resources. SAN connects computers and storage devices using storage protocols, offering advantages like not tying up regular networking bandwidth and allowing dynamic attachment and detachment of devices. The operating system uses hardware efficiently for disk drives by minimizing seek time and maximizing disk bandwidth, which is the total number of bytes transferred over time. Disk I/O requests come from the OS, system processes, and user processes. These requests include various parameters and are managed in a queue, with idle disks immediately working on new requests. Optimization algorithms are used when a queue exists. Several algorithms, such as FCFS, SSTF, SCAN, and CSCAN, are used to schedule disk I/O requests. First-come first-serve scheduling is simple and fair but not very efficient. It can cause wild swings in head movement, as illustrated by the total head movement of 640 cylinders. Shortest seek time first scheduling selects requests with the minimum seek time from the current head position. It can cause starvation of some requests, as shown by the total head movement of 236 cylinders. The scan algorithm moves back and forth across the disk, servicing requests like an elevator. It is also known as the elevator algorithm and can lead to longer wait times for requests at the ends of the disk. An illustration of scan scheduling shows the total head movement of 208 cylinders, highlighting its efficiency in servicing requests. Circular scan improves upon scan by treating all requests in a circular queue fashion, providing a more uniform wait time. The head moves from one end of the disk to the other, then returns to the beginning without servicing requests on the return trip. C-scan scheduling is a disk scheduling algorithm where the head starts at a given position and services requests in one direction until it reaches the end, then jumps back to the beginning and continues. This method ensures a more uniform wait time. When selecting a disk scheduling algorithm, it's important to consider the system load. With very low loads, all algorithms perform equally well. For slightly larger loads, SSTF offers better performance but may lead to starvation. For busier systems, the scan algorithm helps eliminate starvation issues. Disk management involves several key processes including disk formatting, boot block management, and handling bad blocks. Disk formatting prepares the disk for use, while the boot block contains essential startup programs. Bad blocks are managed using methods like sector sparing. Before a disk can be used, it must undergo low-level formatting. This process divides the disk into sectors that can hold data and error correction codes. After low-level formatting, the disk is partitioned and logically formatted to create file systems. The boot block is crucial for starting a computer. It contains a bootstrap program that finds the first sector on the hard drive, loads it into memory, and transfers control to it. This sector, known as the master boot record, helps in partitioning the disk into logical disks. The bootstrap program is stored in ROM and is essential for booting the system. It is stored in the boot blocks of the boot partition, which includes the partition table and boot code. RAID, or Redundant Array of Independent Disks, is a technology that combines multiple physical disk drives into a single unit to improve performance, fault tolerance, and storage capacity. It is a key component in modern data storage solutions. RAID is organized into 6 different levels, each offering varying degrees of performance and reliability. RAID 1, for example, mirrors data to keep duplicates, while RAID 0+1 combines mirroring and striping for high performance and reliability. RAID 0, also known as disk striping, divides data into blocks and spreads them across multiple storage devices. While this improves performance, it also means that if one drive fails, all data is lost. RAID 1, or disk mirroring, involves maintaining duplicate sets of all data on separate disk drives. This provides high data reliability but requires double the storage capacity. RAID 1+0, also known as RAID 10, combines disk mirroring and disk striping to protect data. It requires at least 4 disks and stripes data across mirrored pairs, offering both high performance and reliability. RAID 0+1 requires a minimum of 4 disks and mirrors data across striped pairs. This configuration provides a balance of performance and data protection. There are various RAID levels, each with unique characteristics. These include non-redundant striping, mirrored disks, memory-style error-correcting codes, and block interleaved parity, among others. RAID increases the mean time to failure and mean time to data loss, providing significant reliability. For example, with mirrored disks, the mean time to data loss can be as long as 57,000 years, making RAID a robust solution for data storage. Stable storage technology ensures data integrity by guaranteeing atomicity for write operations. This allows software to be robust against hardware and power failures, making it a reliable choice for critical data storage. To implement stable storage, data is replicated on multiple non-volatile storage media with independent failure modes. Information is updated in a controlled manner to ensure recovery after any failure during data transfer or recovery. The system writes data to two physical disks. The write is considered complete only after both writes are successful, ensuring data integrity and reliability. Disk writes can have three outcomes: successful completion, partial failure, or total failure. Successful completion means data is correctly written, partial failure means some sectors may be corrupted, and total failure means no new data was written.